This video is on Lewis structures. So this is how we can represent the molecules or covalently bonded atoms in two dimensions. The first thing I want you to remember is that compounds form so that each atom has access to 8 valence electrons. That's that octet rule. And that applies for all of those elements except for the little guys. So hydrogen. Hydrogen's going to be happy with only 2. And we've talked about that before. He can be like helium, which is a noble gas, and it fills up his one and only little energy level. Lithium and beryllium are also little guys, so they will often be happy with only 2 valence electrons. Now, we're coming from talking about ionic bonding, and the way we would represent an ionic bond would look something like this, where we have, let's get it without the, there we go. Where you have a chlorine, which has a really strong attraction for the electrons, has pulled the valence electron off of sodium. Sodium develops a positive charge. Chlorine, because it gained an electron, has a negative charge, and it's this positive and this negative that holds the atom together. Now, in ionic compounds, these occur not just one atom to one atom, but lots of cations and lots of anions in that crystal lattice structure. But this is how we would represent an ionic bond. We're going to find that when we represent molecules or things with covalent bonds, they share electrons. And so it's going to look quite different. We're not going to have these charges in there. So again, Lewis structures show how the atoms are arranged in a molecule. And it uses electron dot notations for each element involved. We would get how many atoms are involved from the chemical formula. And the electron dot notation is going to show you how many, or is a way to represent how many valence electrons an element has. Remember that the group number can tell us that from the periodic table. So things in group 1 have 1 valence electron. And things in group 2 have 2 valence electrons. Elements in group 13 have 3, 14 have 4, 15 have 5, 16 have 6, and elements in group 17 have 7 valence electrons. And that corresponds to the number of dots you would draw around an atom. So there are only a few rules when we're writing these Lewis structures. The first one is that we represent covalent bonds, which is a shared pair of electrons, by drawing a straight line. I usually do that in between the 2 electrons that are being shared. The center atom of a molecule is going to be carbon if carbon is present. If carbon's not present, it's going to be the least electronegative element, and that's usually going to be the first element written down. Hydrogen, though, is never the center atom. Hydrogen can only make 1 bond because it only has 1 valence electron, and so it can never be in the middle. Now, knowing those few rules, we can go ahead and draw some molecules here. So let's talk about water first. So with water, we've got H2O. So we've got 2 hydrogens bonded to 1 oxygen. The atom that's going to be in the center is going to be oxygen, because hydrogen can't be in the center. So oxygen on the periodic table is in group 16, which means it has 6 valence electrons. 1, 2, 3, 4, 5, and 6. Now, your drawings here at the very beginning might look a little messy, and it's also a whole lot easier to draw Lewis structures with a pencil than with a pen, because you might have to do some erasing. So the first part of this is going to be about exposure. I've been drawing molecules for 2 decades, so I'm very used to this, and I know how the molecules and the Lewis structures should look. You haven't been drawing them for nearly that long, so it's going to take a little bit of time for you to get used to it. This is often how I will draw something with 6 valence electrons. And especially, I know that bonded to this oxygen, I have 2 hydrogens. So I left these 2 electrons not paired up to kind of give me a spot for bonding. So now I'm going to add in my hydrogens. The hydrogens are in group 1, so they have 1 valence electron. All right. Now, these electrons right here are the 2 that are going to be shared. And so we'll represent those as a line. Then we need to stop and check to make sure everyone's happy. Because remember that atoms form molecules in order to become more stable. And if they can't become more stable, they're not going to bond to one another. So let's count the oxygens or the electrons that oxygen now has access to. 1, 2, 3, 4, 5, 6, 7, 8. So oxygen has access to 8 valence electrons. That fulfills its octet, so oxygen's very happy. Each hydrogen has access to 2 valence electrons. So when you're counting the lines, you need to count them as 2 electrons because it is a shared pair of electrons. And hydrogen's happy with 2. So this is the correct structure for water. Let's look at something else for, let's say, CH4. So carbon is present, so it's going to be in the middle. Carbon is in group 14, so it has 4 valence electrons. And often this is how I will draw 4 valence electrons. And especially when I know that I've got 4 things that need to bond to this carbon. It kind of gives me 4 spots for bonding. So then I'm going to bring each hydrogen in with its 1 valence electron. And these are the electrons that are going to be shared. So we'll draw them as a line to represent the bond. Okay, let's make that one a little more bold. Then we need to check and make sure that everyone's happy so that we can be sure that we drew our structure correctly. So carbon now has access to 1, 2, 3, 4, 5, 6, 7, 8. That makes him happy. It fulfills that octet. And each hydrogen has access to 2, and that makes them happy. So that is the correct structure for methane. Let's look at another one. I've got NH3. So nitrogen is going to be in the center. It's the first one written, and hydrogen can't be because it only makes 1 bond. Nitrogen's in group 15, so it has 5 valence electrons, 1, 2, 3, 4, and 5. So this is often how I will draw the electron dot structure for something that has 5 valence electrons. It gives, especially when it has 3 things that it needs to bond to, and I have 3 spots for bonding. Each hydrogen is going to come in with 1, and they're going to form a bond. Then we check to make sure everyone's happy. Nitrogen has access to 1, 2, 3, 4, 5, 6, 7, 8. That fulfills his octet. And each hydrogen has access to 2 valence electrons, and that makes him happy. If we were bonded to something other than hydrogen, so let's look at this one. Phosphorus triiodide. Phosphorus is in group 15, so it has 5 valence electrons, 1, 2, 3, 4, and 5. And then I'm going to have 3 iodines. Iodine is a halogen, and it has access to 7. So 1, 2, 3, 4, 5, 6, and 7. Sorry, it has 7 valence electrons. And then each iodine is going to be the same way with their 7 valence electrons. Oops. Seven. And this is going to form a bond here. And now phosphorus has access to 1, 2, 3, 4, 5, 6, 7, 8. That fulfills his octet. Iodine now has access to 1, 2, 3, 4, 5, 6, 7, 8. And each iodine has access to 8. Everyone has fulfilled their octet, and so we know that is the correct structure. Now, sometimes it requires more than one set of electron pairs have to be shared in order to satisfy the octet rule. And that's how we know we're going to need multiple covalent bonds. So what I have shown you down here are all single bonds with the sharing one pair of electrons. A multiple covalent bond is where they're going to share more than one pair. And so if they're sharing two pairs of electrons, that would be a double bond. And if they're sharing three pairs of electrons, then it's going to be a triple bond. Now, the more electron pairs shared between two atoms, the more energy is required to break them. So if you have a double bond is more difficult to break than a single bond. And a triple bond is really, really strong and requires much more energy to break than a double or a single bond. So the more electron pairs they share, the more energy is required to break those. So we'll call it a stronger bond. It also, the more electron pairs two atoms share, the closer the atoms end up to one another. So if we've got a certain length for a single bond, and then we go to form a double bond, those atoms are going to be held a little closer to each other. And a triple bond is the shortest of the bonds. You're sharing three pairs of electrons, so it pulls those atoms in closer and closer. This is a really important little statement here. You will see test questions on this one little sentence. So just remember, more bonds are stronger and shorter. So a double bond, atoms that like to double bond are carbon, nitrogen, and oxygen. I say that those three form multiple bonds. And triple bonds are the strongest and the shortest. And you have to watch out for carbon and nitrogen. They will often triple bond. Well, how do you know if you need to have a multiple covalent bond? I'm going to show you an example. And this is how you'll know how to do these. The example we're going to work with is carbon dioxide. So it's carbon and two oxygens. Carbon is going to be the atom in the center, and carbon's in group 14, so it has 4 valence electrons. Oxygen is in group 16, so it has 6 valence electrons, and there are 2 of them. So I'm going to put one oxygen here. It has 6 valence electrons, 5 and 6. I got to bring one up there so I can actually bond these 2. Then we're going to find that if we put one oxygen on this side, the other oxygen has to be as far away as possible. 2, 3, 4, 5, and 6. Again, 6 valence electrons because it's in group 16, and then we're going to bond. Then we check to see if everyone's happy. Oxygen only has access to 1, 2, 3, 4, 5, 6, and 7, not a full octet. The same is true for this oxygen. This carbon only has access to 1, 2, 3, 4, 5, 6. It only has access to 6 valence electrons. No one's happy in this situation, and atoms aren't going to bond if they can't be happy and stable. That's what's in it for them. So this is not the correct structure for carbon dioxide. They're going to have to share more than one pair of electrons in order to fulfill their octets. So what's going to have to happen, and I'm going to draw these arrows, but they're only for emphasis. This electron from oxygen is going to move, and this electron from carbon is going to move, and those two are going to participate in another bond between the two atoms. Now, once you've moved the electrons, you need to go ahead and erase them, and that's why I said it's much better to do this in pencil, but also dry erase markers work really well. All right, now we can see that this oxygen over here has access to 1, 2, 3, 4, 5, 6, 7, 8. This oxygen's all nice and happy, but this carbon only has access to 7, and the same is true here for this oxygen. So these two are not happy. What's going to happen is the same thing on this side. This electron from oxygen is going to move up, and this electron from carbon is going to move, and they're going to create another bond. Now, again, I only draw these arrows for emphasis. Once they are moved, make sure that you erase them. Otherwise, it messes up your electron count. So now I have Carbon has access to 1, 2, 3, 4, 5, 6, 7, 8. He's nice and happy. And this oxygen also has access to 8 valence electrons. This is a happy, stable molecule, and this is the correct structure for carbon dioxide.